Good afternoon to everybody. My name is Alberto Bertucco. I'm the director of the Center Levi Cases for Energy, Economics and Technology at the University of Padova. And today we are here for the third event of this spring program of our center. And I'm very pleased to announce that this event has been co-sponsored by University of Padova and University of Trieste, where a similar center is operating. Today is for us honor and pleasure to host a special lecture by Professor Mark Jacobson, who is the director of the Atmosphere Energy Program at the Stanford University in California. So I would like to thank Professor Jacobson very much for this lecture, and the program of this afternoon is very simple. There will be the lecture by Professor Jacobson, and at the end we can ask questions. However, the total allotted time for this event is 1 hour and a half, so by 4 o'clock Italian time everything will be finished. So all of you who would like to ask a question to Professor Jacobson are kindly invited to write in the chat their name and the question. Okay, in the end, here from the control room, we will enable the people to make the question. All right, so that's all for our organization. Please, Mark, the stage is yours, and whenever you like, you can start with your lecture. Thank you again. Yes. One moment, please. One moment, please.
Maybe he has to unmute.
Okay.
There we go. Hello, everybody, and thank you very much for the kind introduction. Today, I want to talk about transitioning countries and states and cities and towns all entirely to clean renewable energy to address climate change and air pollution and energy insecurity. And so let's look at there are three main reasons that we're focusing on a 100% clean renewable energy in these solutions. One is air pollution, which causes about 7 million deaths per year worldwide. And most of these are due to particles in air pollution. 90% are due to particles. And most of these deaths are also in developing countries, and less than half are due to indoor air pollution from indoor burning of biofuels and solid fuels, including biomass, dung, and wood, and also some coal. But the cost of air pollution is on the order of $30 trillion per year based on statistical cost of life. Global warming is a rising problem and is already causing significant damage and is estimated to cost on the order of $30 trillion per year also by 2050. There are also several types of energy insecurity issues. There are actually 4 types of energy insecurity issues we're trying to address through these clean renewable energy plans. Well, the first is the fact that fossil fuels and uranium are very limited resources and will run out over time, and that will result in energy price instability, and that will result in political and social instability as well if we don't have a replacement. The second type of energy insecurity is the fact that we have a lot of centralized power plants and refineries, and that creates chaos when one of them goes down. If a large power plant goes down, then large sections of a city can lose power, whereas more distributed energy makes it more difficult for large sections of a city to go down if one wind turbine or one set of solar panels goes down on the grid, whether it's due to maintenance problems or due to terrorism or something else. The third type of energy insecurity problem is the one where we're seeing play out in front of us today, which is when one country has significant control of the supply of fossil fuel, usually of another country. So for example, Russia has a significant supply of natural gas that it supplies to Europe. And that when you have conflict like you do today, that can lead to either being the fuel being held hostage, or in this case, sanctions being imposed, and that causes costs to rise for everybody due to the lack of the fuel. But it's not only the international trading of fuels that and the long distance transport, the long distance exchange of fuels that is a problem. It's also long distance transport. Like there are many island countries that rely on the transport of fossil fuels for their energy. And this causes costs to rise significantly. For example, in American Samoa, the cost of electricity is over 50 cents per kilowatt hour compared to less than 20 cents a kilowatt hour in the US mainland. Even Hawaii has a cost of electricity that's over 35 cents per kilowatt hour because you have to transport fossil fuels, oil and gas mostly, long distance, or in diesel. A lot of island countries use diesel fuel. So that's the third type. And the final type of energy insecurity we're trying to solve is just the risks of fossil fuel and nuclear infrastructures. With nuclear, we have meltdown risk, waste risk issues, weapons proliferation risk, uranium mining risks for lung cancer. For fossil fuels, we have mining risks and air pollution impacts. So these are additional energy insecurity risks that we can avoid if we transition to clean renewable energy. So our idea is to electrify all energy sectors or provide direct heat for some energy and provide the electricity and heat with entirely clean renewable energy, namely wind and water and solar power. And we define wind, water, and solar as onshore and offshore wind, solar photovoltaics on rooftops and in power plants, concentrated solar power, solar thermal for heat, hydroelectric power, geothermal power we consider part of the water just because we want to keep a simple acronym, and tidal and wave power as well. So that's and then some geothermal heat as well. So those are the sources of electricity and heat. And we would electrify all transportation. So using either battery electric or hydrogen fuel cell vehicles, where hydrogen fuel cell vehicles would be limited to large, long distance heavy transport. So long distance aircraft, long distance ships, long distance trains and some trucks, but not passenger vehicles, for example. And speaking of hydrogen, we only support green hydrogen, which is hydrogen produced from wind, water, and solar through electrolysis. And the only applications of hydrogen we support are long distance heavy transport, for steel production and some other industrial processes, and providing electricity and heat for some remote microgrids. But we do not support hydrogen for passenger vehicles, small vehicles, for home heating, or for grid electricity, because batteries are just much more efficient for grid electricity storage than is hydrogen storage. And you just need a lot more renewable energy sources to produce that hydrogen and then to store it and then to use it in a fuel cell than you would to run it through a battery. For buildings, we would electrify those with heat pumps, replacing natural gas heaters for air heating and also cooling. And we'd use heat pump water heaters for water heating. We'd use electric induction cooktops for cooking. We'd replace all gas appliances in homes with electric equivalents. We'd have some district heating and cooling, and then there'd be some geothermal and solar direct heat. For industry, we'd electrify that as well with electric arc furnaces, induction furnaces, resistance furnaces, dielectric heaters, electron beam heaters. These are all existing technologies. In fact, we have over 95% of the technologies we need to transition the world for all purposes. The technologies we don't have right now are long distance aircraft and ships, which would probably run on hydrogen fuel cells, but we know how to do that. So it's really a question of implementing those. And also we don't have some industrial processes transitioned yet commercially. So, but again, we know how to do that. Now we'll need storage with 100% clean renewable energy, and we need electricity storage, heat storage, cold storage, and also hydrogen storage. There are many electricity options already available: concentrated solar power with storage, pumped hydro storage, existing hydroelectric dams are a form of storage, batteries, flywheels, compressed air, gravitational storage of solid masses. These are all existing technologies. For heating, cooling, well, the most common type of storage worldwide for both is water tank storage. There's also ice storage for cooling. And then for heating, there's underground borehole, water pit, and aquifer storage. Aquifer storage has also been used for cooling storage as well. And then in building materials. And then hydrogen is a form of storage, as I mentioned. Now, I'll just give you some examples of some types of storage that are being used. Stanford University, actually where I work, is now 100% renewable for all buildings, as well in terms of electricity, but also in terms of heating and cooling. So it's actually now the first university in the world to be 100% renewable for heating, cooling, and electricity. And what they did was in 2016, 80% of the campus electricity and heat was powered by natural gas cogeneration. That was bulldozed and replaced with a fourth generation district heating and cooling system, which you can see here. There were about 35 miles of cooling pipes and 35 miles of heating pipes laid around the university. There are 2 chillers and a boiler, which you can see here. And there are heat pumps that raise the temperature of the hot water and lower the temperature of the cold water. The heat pumps run on electricity, and so provide the heating and cooling for all the buildings through district heating and cooling system. And then the university purchased on the order of 150 megawatts of solar photovoltaics in 2 power plants in California, and 10 megawatts of that is on rooftops on the university campus. So from the solar photovoltaics powering the electricity and powering the heating and cooling for these fourth generation heating and cooling system, the university is now 100% renewable, which is good news. This can be replicated in many universities, not only, but also other types of facilities where you have large numbers of buildings. Another type of district heating system is underground borehole storage. This is a community in Okotoks, Canada, which is north of Calgary, where it's very sunny during the summer, where the days are long. So in 2004 and 5, there were 52 homes built with these solar collectors on the roofs of the garages, as the top left photograph. And in those solar collectors are a glycol solution. During the summer, the glycol solution gets heated and piped to this building on the right, where the heat gets transferred to water. The water is then piped underground, where there were this field is excavated and filled with U-shaped pipes that go down about 30 meters. The hot water then it exchanges its heat with the soil to heat the soil. The soil gets heated up, and the soil was covered with this field where children play on, and that heat gets stored until wintertime or whenever it's needed. And when the snow is on the ground in the wintertime, like on the bottom left, then the whole system is run in reverse, and that heat is extracted from the soil and sent by water first to the building, but then back to the homes, and provides 100% of the heating, wintertime heating for these 52 homes. And this is really actually inexpensive storage. It's not very efficient. It's about a round trip efficiency of on the order of 56%, which sounds not very efficient, but the cost is so low, it's less than $1 per kilowatt hour of storage compared to, this is heat storage, but batteries, for example, are $100 to $200 per kilowatt hour of storage. So it's very inexpensive storage, and it provides reliable heating for these homes. Here's another type of district heating system. This is in Vogens, Denmark. It's water pit storage. So on the left is a big swimming pool-like structure that's filled with water and covered with insulation. And during the summer, these solar collectors will collect heat and heat the water up to 80 degrees Celsius. And that water gets stored until wintertime, where it provides heat for the 2,500 homes in this town. So, and then one more type of kind of district cooling storage. This is ice cooling. actually, in 1998, my university also had a big ice cube under a building such as this. And during the day, in the summer, when it got very hot, uh, instead of using air conditioning, which requires electricity and causes blackouts in California, because that's when the most electricity is used, is in the hot summer afternoons. Instead of doing that during the night, when electricity prices were low, water would be, or ice would be formed, such as this. And then during the day, when cooling was needed, water is run through the coils in the ice and then sent to the buildings to cool the buildings, and instead of using air conditioning. And this requires no electricity here during the day. So this is basically like battery electric storage, because it serves the same purpose as a battery, but it costs less than $40 per kilowatt hour versus now $100 to $200 per kilowatt hour for batteries. Okay, so before I talk about plans for Italy and the world to run on 100% clean renewable energy, I want to talk about transitioning an individual home. And I'm going to talk about my own home, which I built in 2017. And I made sure there was no natural gas on the property. It's all electric, and it powers itself in the annual average. In fact, it more than powers itself. There are 13.6 kilowatts of solar PV on the rooftop. And I have 4 Tesla wall mount batteries. These are first generation. So each one is about 3.3 kilowatt peak discharge and around 6.6 kilowatt hours of storage capacity, which means that the storage, if you're discharging it at its peak, it has 2 hours of storage. But because there are 4 of them, it's really flexible in the sense that you can either discharge at 3.3 kilowatts for 8 hours, because you just run one after the other. So they're basically concatenated together to provide either 8 hours of storage at 3.3 kilowatts, or you can run 13.2 kilowatts for 2 hours. So that's why these concatenated batteries are very flexible way of storing power. In fact, you can imagine either 2-hour batteries or 4-hour batteries, both of which exist. And let's say you have 25 4-hour batteries. That gives you 100 hours of storage. Or if you have 100 4-hour batteries, that's 400 hours of storage. So we already have long duration electricity storage simply by concatenating batteries together. And the advantage of that is you can also run them simultaneously. So if you have 100 4-hour batteries and each one, let's say, has a peak discharge rate of 10 kilowatts, 100 times 10 is 1,000. So you have 1,000 kilowatts of instantaneous storage or instantaneous release potential for 4 hours, or you have 400 hours of storage at 10 kilowatts or anything in between. So this is really important for keeping the grid stable. One of the ways to keep the grid stable is basically just using 4-hour batteries and concatenating them. And in fact, that's what I'm going to show you later, that's how one of the ways we keep the grid stable in any country in the world. Now, for heating and cooling, I have heat pumps, and this is for air heating and cooling. So these are called ductless mini split heat pump air heaters and air conditioners. So there are no ducts to send heat through the building. Instead, in each room, there's one of these devices, like on the left, near the ceiling, and so let's say I have around 10 or 11 of these, and then there are 2 outside units, like on the right, which exchange heat with the air outside. So these are air source heat pumps, and the only connection is there's a tubing pipe that contains coolant that between each of the indoor units and the outdoor units. So heat pumps are great because they don't create heat or destroy heat. They just move it around. And as a result, they use 1/4 the energy as a natural gas. Advantages. Now, for water heating, it's similar. I have a heat pump water heater that runs on electricity, and the air source heat pump also runs on electricity. And this is just like a gas water heater, except that there's no gas. And so it runs on electricity, and it exchanges heat with the air inside this mechanical room. So the room itself gets a little bit cooler, during the day, which is fine during the summer because then I open the door to the room and let some of that cool air out. But the temperature does not get really cold. It's just a few degrees cooler. And again, it's very efficient. It uses 1/4 the energy as a natural gas heater, and it doesn't require pipes, except, I mean, it doesn't require natural gas pipes. It just requires water pipes. So very efficient and works really well. For cooking, I use an electric induction cooktop. This is actually not the same as electric resistance. Most people do not like electric resistance stoves, but the electric induction cooktop is much better. It boils water in half the time as natural gas. When you touch the stove, even when you're boiling water, it does not feel hot. It's just warm because you're not producing heat in the stove. What's going on is you're exciting molecules in the bottom of the pot or the pan. And so the base of the pot or the pan has to either be iron or stainless steel, which has high resistance, because you basically create resistance with electricity currents. You create resistance in the pot or the pan, so the pot or the pan gets hot, and that cooks the food very evenly, whereas the stove itself does not get hot. So it works really well. And I show an individual burner on the left. Now that burner costs on the order of $60, could be even down to $40. And I show that because, as I mentioned earlier, in developing countries, a lot of people cook with wood or dung or biomass, other type of biomass or coal, causing lots of air pollution, health problems, and death. And we can replace all that type of cooking with a single burner, as I mentioned, that runs on electricity. And as it's very inexpensive. Now you need an electricity source, of course. And so that's where having a few solar panels or community solar will really help. Having some batteries, creating microgrids in remote communities is a way to solve this problem, air pollution and energy problems associated with burning things. This shows results of 4 years of energy use in my home. And actually I'm finished now almost 5 years. And I have even better results this year. But over the 4 years, I generated 120% of all my home and vehicle energy from the solar on the roof. So I have 2 electric cars as well. I've had no electric bill, natural gas bill, or gasoline bill during this period. For the extra solar electricity, I sold it to a community choice aggregation utility. These are utilities that are available in California and several other states that will not only provide you with 100% renewable electricity if you do not have your own solar, but will also purchase extra solar from you at the cost that they would charge you if you're using that solar. Now, I avoided, not only do I get paid for the extra electricity and do I not have any bills, but I also avoided during construction the need for gas pipe. In my case, it would have saved about $10,000 to $12,000, but I show a range here of $2,000 to $15,000 depending on your size of your house. There's a gas hookup fee that it was avoided. It was about $6,000. Then I have the savings of all those electric and natural gas and vehicle fuel bills. So a total of $5,000 to $23,000 up front for your average home, plus another $3,000 to $10,000 per year. And then there are subsidies available in many places. With subsidies, the payback time is 5 years. Without, it's about 10 years. But the solar is warranted for 25 years. So this is really everybody should be doing this. It's so efficient to use electric appliances these days. And this shows an example. So on the hottest day of the year in 2020, the outside temperature, I'm sorry that I'm using Fahrenheit here, but everything here is in Fahrenheit. The outside temperature was 106 degrees on the hottest day of the year. I kept the inside temperature 77 degrees Fahrenheit. And you can see on the right that the green was my solar production that day. The blue was during the day was the electricity production from solar that was used for home use. Most of that was for the heat pumps to keep the house cool. But you can see it's not using a whole lot of electricity to keep the temperature 30 degrees Fahrenheit below the outside temperature. The nighttime blue is from the batteries, and then the red is when I needed grid electricity. But you can see from the data here that on that day, over the 24 hours, I generated 12 kilowatt hours more than I consumed. So on the hottest day of the year, I'm actually a net producer of electricity while keeping the home perfectly comfortable. if everybody were doing this, there would be no blackouts in the state. This is a time of year when blackouts will occur. Okay, so next step is to look at, can we transition, actually I should have said Italy in the world, to 100% clean renewable energy for all purposes. And so I'm going to talk about new roadmaps we've developed for 145 countries, including Italy. And this shows for all 145 countries, the 2018 end-use power demand was about 13.1 trillion watts or terawatts. That's expected to go up in a business as usual case to 20.4 terawatts by 2050. But if we electrify all energy and provide the electricity with wind, water, and solar, the energy requirements go down about 56%. And you might ask, how does that occur? And this is without people changing their habits. Well, it's because battery electric and hydrogen fuel cell vehicles are more efficient than internal combustion engine vehicles. Like an individual battery electric vehicle uses about 1/4 the energy as an internal combustion engine vehicle. Hydrogen fuel cell is not quite so efficient, except when you get to long distance heavy transport, then it actually becomes more efficient than battery electrics. But overall, all types of transportation, there's a 20.5% reduction of energy use compared with business as usual. There's another 4.3% reduction of energy requirements due to electrifying industry, 13.6% due to the efficiency of heat pumps for heating and cooling versus natural gas heaters and oil-based heaters. And then 11% of all energy worldwide is used to mine, transport, and refine fossil fuels and uranium, and that's eliminated. And then we get another 6.6% due to energy efficiency improvements beyond what's expected in business as usual. So that adds up to 56.4%. So this is another way of looking at that. This goes from 2020 to 2050 on the horizontal axis. And if we do not do anything, we go along the very top line to the business as usual, on the business as usual trajectory. But then if we electrify all energy and provide the electricity with wind, water, solar, we go down those 5 shades of colors down to the 100% WWS line. So each of those reductions represents the number I showed in the last table. And then we'll provide that wind, water, solar with certain percentage of onshore and offshore wind, utility PV, CSP, solar heats, rooftop PV, geothermal, heat and electricity, hydroelectric, and tidal and wave. And this shows the average over, or this, well, yeah, the average over all 145 countries. Now, this is if we transition by 2050, 100%, with 80% by 2030. This is kind of what a transition line would be like. But we really need to transition even faster. Well, if we do this transition line, this will, according to IPCC, will avoid 1.5 degrees warming. The key is, to get 80% transition by 2030, well, that's 8 years away. Then so that's we would need to rapidly transition all energy sectors and eliminate all non-energy emissions simultaneously. So that's a big asking, but it's possible. So along this trajectory, we can avoid 1.5 degrees if we do this. We can even do it faster. This shows the same result, but 80% transition by 2030 and 100% by 2035 across all energy sectors. The endpoints in 2050 is still the same, but this shows a faster transition. So somewhere in between is hopefully, I mean, if we can get 80% by 2030, that would be awesome. But that's what we should shoot for. That's the minimum we should shoot for, I believe. And we should also shoot for 100% by 2035, if possible. Doesn't mean we will actually get there, but if we don't try, we definitely won't get there. Now, if we look at the worldwide, if I average over the 145 countries, the production of the energy would be about, this is just one set of scenarios, worldwide about 32% onshore wind, 13% offshore, 16% rooftop PV, 30% utility PV, less than 3% CSP, less than 1% geothermal electricity, almost 5% hydro, all of which exists, and then tiny amounts of tidal wave and some geothermal heat and solar heat. For Italy, there's a little more onshore wind and offshore wind, and some rooftop and utility PV, CSP. You can see the numbers. Again, this is just one scenario, that results in a stable grid in Italy. But you can imagine there are other scenarios with maybe less onshore wind, more solar or utility PV. And so a lot of the limits are, you might ask, why isn't there more utility PV? Well, it's just because we're trying to limit the land area required. And so if there's more rooftop PV, that would be great. That doesn't take up new land, but more utility PV will take up more land. We want to keep the land requirements under a few percent. So I'll show you that in a minute. But yeah, so here, in fact, is the land requirements. Worldwide, well, offshore wind does not take up new land. Tidal wave do not take up new land. This shows new land required in addition to what's already being taken up by renewables. Hydro, in our plans, we have no new hydro added. Now, it's not that we don't object to new hydro, but we're assuming that there won't be new hydro in the average. So there's no new land for that. Rooftop PV does not take up new land. There's not a whole lot of geothermal. So the new land is basically utility PV plus CSP and onshore wind. And on a worldwide scale, that land area required for the onshore wind is about 0.36% of all world land area. And for utility PV and CSP, that's called footprint on the ground, that's about 0.17%. So for onshore wind, that is spacing in between wind turbines, which is open space that can be used for multiple purposes. That's why they're separated out. The onshore wind land is mostly open space that has dual purpose. The utility PV and CSP is pretty much footprint that you can't use for other purposes. However, you can put some of that PV in between wind turbines so that some of that 0.36% can be occupied by the utility PV plus CSP land. So this 0.53% total is the maximum, and most of that land actually has multiple purposes. Now for Italy, you can see the numbers are a bit higher. Onshore wind is close to 2%, and utility PV plus CSP, it's 0.24%. So we could reduce onshore wind, increase utility PV. As I said, there are multiple ways to do this. This was just one scenario for Italy. And this is an example of keeping the grid stable. So we broke up those 145 countries into 24 world regions. And so Italy was in the Europe region. I could have showed Europe here. But then we looked at matching supply demand, well, matching demand for electricity and heat for all purposes with generation, storage, demand response every 30 seconds. So this is a very high resolution and time model. So every 30 seconds here for 2 years. And this shows that we can match demand every 30 seconds. And on the bottom, it shows, well, both of these graphs show the results every hour, but we didn't do it down to 30-second resolution. But you can see we're matching demand with supply, storage, and demand response exactly every 30 seconds for 2 years everywhere in the world without any blackouts whatsoever. And this is using meteorological data for the wind and solar from a climate model. So it's predicting the wind and solar radiation every 30 seconds for 2 years everywhere in the world. Now, you might ask, well, what's the cost of energy? And these are the costs basically of a Green New Deal, either worldwide or in a given country. So in terms of the cost per unit electricity produced or heat produced, it's on the order of 8.3 cents per kilowatt hour worldwide. US is about 8.7 cents, China is about 7.6 cents, Italy was about 8.4 cents a kilowatt hour. And you can see the capital costs also 61.5 trillion for the world, about 7 trillion for the US, 13 trillion for China, is on the order of 6 trillion for Europe, and 545 billion for Italy. So that's what it costs to transition everything for all purposes to eliminate air pollution, to eliminate this 7 million air pollution deaths per year, to eliminate emissions associated with global warming from energy, and to provide energy security for all these places. Now, this is another way to look at the costs, which are the annual cost of energy. So worldwide in 2050, the annual fuel cost is going to be about $17.8 trillion per year. Today, it's on the order of $12 trillion per year. But the health cost is $33.6 trillion per year. That's the 7 million deaths plus hundreds of millions more illnesses per year from business as usual combustion, particles and gases. And then the climate cost is about $32 trillion per year. So a total of $83 trillion per year is the social cost of fossil fuel energy. we eliminate with wind, water, solar, we eliminate the health costs, we eliminate the climate costs, we reduce the energy requirements 56%, but then we reduce the cost per unit energy another 10%. So that gives us a 63% lower energy cost down to 6.6 trillion per year from 17.8, and a social cost reduction of 92%. So that's really the benefit of transitioning to 100% clean renewable energy, eliminating health costs, climate costs, and substantially reducing energy costs, and providing energy stability, eliminating these 4 energy insecurity issues that I mentioned before. Now, just a little bit on policies. So we started developing these 100% renewable energy plans back in 2009 with actually this paper, which was looking at, can we power the world with just 100% wind, water, and solar? And that was really, it wasn't looking at grid stability. Didn't do the modeling, did some analysis for grid stability, but just looking at the annual average. And the conclusion of this study back then was, yes, it's technically and economically possible in terms of resources, in terms of costs, in terms of the land areas available for renewables, and in terms of materials. It's technically and economically possible to transition to 100% renewables worldwide by 2030, but for social and political reasons, that's not likely to happen. It's more practical to think of an 80% transition by 2030 and 100% by 2050. Little did we know that this would be the basis for the Green New Deal proposals in the US to go to 100% renewables by 2030. And they've made their way into other countries as well. But since then, there's 61 countries have committed, either through laws or other types of commitments, to 100% renewable electricity. However, only one country, Denmark, has committed to 100% renewable energy for all energy. So all these other countries have not committed for the transportation, buildings, industry, and most of these are small countries. Big countries of the world have not committed as well. But there is progress. There are 13 countries that are actually near or above 100% renewable electricity production in their annual average. Most of these generate mostly hydro. So Iceland, Norway, Costa Rica, Paraguay, Uruguay, Tajikistan, Albania, and Bhutan, Nepal, Ethiopia, and the Congo all generate most of their electricity from hydro. Scotland is mostly wind. Kenya is mostly geothermal. But the good news is there are many countries that are either very close or over 100% renewable electricity in their annual average. And this is encouraging, although we need the bigger countries, because the emissions alone from China are equivalent to the emissions of 120 countries that have low emissions. So China is going to take care of 120 countries worth of emissions if we can transition. Now, in the US, there are actually 18 states and territories that have laws or executive orders to go to 100% renewables. And these include Rhode Island by 2030, Washington, D.C. by 2032, Connecticut and Oregon by 2040, and most of them Hawaii, California, New Mexico, Washington State, New York, and Illinois by 2045. Then Puerto Rico, Nevada, Maine, Wisconsin, Virginia, New Jersey, North Carolina, and Nebraska by 2050. So that's great news that there are a lot of commitments, but again, this is just electricity, not all energy, and it's not all states. There are 180 US cities, including most of the major cities in the United States, that have committed to 100% renewables. Worldwide, there are over 400 cities that have committed. And so that's the first step, is to have a commitment, and then they actually have to do that. There are 300, now even more, but 340 companies at least that have committed to 100% renewables, including 8 of the 10 biggest companies in the world, which are in blue there. And this is important because these companies are actually purchasing wind farms and solar farms and building them to offset their operations. So these are actual real renewable projects that are going up. And so we see a lot of growth of renewables in many countries and worldwide. In fact, there's a new study saying that 10% of all world electricity as of this year is produced from just wind and solar alone. And that's for the first time. So there's this big growth of renewables, particularly wind and solar in many countries. And a lot of that growth is driven by companies that are purchasing solar or wind farms to offset their energy use. Now, okay, so to summarize, I didn't talk about jobs, but I'll just mention them briefly here. We did analyze jobs in all 145 countries, and we found that we would create 28 million more long-term full-time jobs than lost by transitioning. These are a combination of construction jobs and permanent operation jobs. Keep in mind, let's say we're continuously, let's say a wind turbine lasts 30 years, and just simplistically, let's say we develop 1/30 of all the wind farms we need every year for 30 years. Well, we'd create 30 years worth of jobs, but then after 30 years, we'd start to have to replace wind farms with new ones or refurbish them, and so we'd have continuous jobs after that. So this whole infrastructure will create jobs for a long time, and more jobs than are lost. As I mentioned, we'd require only 0.17% of all land for footprint, and that's for the solar, and only 0.36% for spacing worldwide. Now, in comparison, in the United States alone, 1.3% of all US land area is occupied by the fossil fuel industry. That's for millions of miles of oil and gas pipeline. There are 1.3 million active oil and gas wells. There are 3.2 million abandoned wells. There are hundreds of thousands of gas stations. There are refineries, there are storage facilities, there are coal mines. All the fossil fuel industry takes up 1.3% of land. In the US, the land area required for wind, water, solar is less than 1% of the land, including lots of spacing. So we'd actually reduce land use. Another thing people are worried about are materials and in mining. Sure, we'll have to mine for lithium, we'll have to mine for neodymium and we'll need a lot of steel and concrete, but we're reducing the mining substantially by going to clean renewable energy, because with fossil fuels, you need to not only mine materials for the infrastructure, but also you have to mine for the fossil fuels themselves continuously forever. And so with renewables, the wind comes right to the turbine, the solar comes right to the panel. So we do not need to mine for the fuels, only for the infrastructure. So we have orders of magnitude less mining. Doesn't mean we eliminate mining, but we have much, much less mining. In the US, well, North America, there are 50,000 new oil and gas wells drilled every year. And that, as I mentioned, takes up a huge amount of land area when you add it all up. And so we eliminate all that mining and replace it with some mining, but much less mining for raw materials. The other conclusion here, we'd eliminate 7 million air pollution deaths per year from energy, slow then reverse global warming. We keep the grid stable throughout the world with 100% clean renewable energy. We reduce absolute energy costs by 63% worldwide, and health plus climate plus energy costs by 92%. And if you are interested in more information on this, then here are some links, and including the book that was mentioned earlier that really describes everything that I've been talking about and plus a lot more, and even discusses all the energy plans. And I update a lot of stuff on Twitter, all the more recent information. So with that, I'm happy to answer any questions you might have, but thank you so much for listening. So.
We'd like to thank the lecturer. And now, as I said before, everyone is invited to put questions in the chat, and from this room, we will start with the question for you. So I just ask Francesco Suman to start with this.
Puoi attivarmi l'audio? Okay, can you hear me, Mark?
Yeah.
I'm here in the room.
Yeah, I can hear you.
Okay. Very interesting question.
Yeah, I think you might be muted.
Okay, you cannot hear me from the environmental audio? Okay, maybe I'll come closer to the.
Still muted.
Okay.
Can you hear me now?
Yeah, okay, yeah. I can hear
Okay, better. Well, so I invite people in the room who want to ask some questions to Professor Jacobson to come closer to the microphone in order to, be audible. Instead, I suggest people from the audience connected via Zoom, they can type their questions in the chat box. Alternatively, they can raise their hands with their raise your hand tool in Zoom, and we can unmute you, and so you can speak and ask your questions directly to Mark. So, if there are already some questions from the audience, both from the room or from the Zoom platform, you are invited to raise your hand. In the meantime, to break the ice, I can ask a question to you directly, Mark. It will be, let's start with a less technical question. Maybe there will be others in the discussion. Let's say it is something connected to recent events, ongoing in the world recently. But first I will start asking you if you're happy with the ongoing climate policies in your country, in the US. I mean, has Joe Biden kept his promises on clean energy spending? How is the climate bill going? Because I know there were some problems in the Congress there, and maybe things didn't went how you expected. Can you tell us something about that?
Yes, well, certainly it's better than it was a couple of years ago, but I'm not totally pleased because many years ago with President Obama, there was a policy called all of the above, where we just try a little bit of everything and hope it works. And that has actually just been adopted again. So President Biden and his cabinet or his energy advisors are really proposing to use a lot of technologies that we do not think are very helpful. So we do not, I'm focused on wind, water, and solar, so clean renewable energy, eliminating combustion. But there are many who push carbon capture, direct air capture, biofuels, biomass, bioenergy, and nuclear. So all of these, most of those are combustion. So when you use carbon capture, you're burning fossil fuels, and then you try to capture the CO2. But all the other air pollutants go right to the air, and you have more of those air pollutants because you need more energy, and so you burn more fossils to get that energy. So, for example, there was one carbon capture plant attached coal plant in the U.S. starting in 2016. It was in Texas. They had a coal plant and they added carbon capture. But to run the carbon capture equipment, they had to build a natural gas plant just to provide the electricity to run the carbon capture for the coal plant. That increased the energy use overall by 25 to 50%. And there was more natural gas mining to provide the energy. None of CO2 from the natural gas plant was captured. And the efficiency of the capture was only 70% from the coal plant, but it did not capture any CO2 from the upstream mining of the coal or the natural gas mining. And this is before you looked at what happened to the CO2 after it was captured. So when you actually added up all the numbers, only 11% of the CO2 emitted from this whole system was ever captured. Of that, it was all sent to a nearby oil field to enhance oil recovery. That resulted in 40% of that CO2 that was captured going right back to the air, and then more oil, which has also burned more air pollution. So what happens with carbon capture? You have more air pollution, more mining, more fossil infrastructure, hardly any CO2 benefit. So it's a big smoke stream. Same thing with direct air capture, the same thing with blue hydrogen. And when you're burning bioenergy, biomass, biofuels, you're producing air pollution. You're not reducing much carbon. Problems with nuclear, of course, are it takes 17 to 20 years these days between planning and operation of a nuclear plant. There's only one being built in the U.S. in Georgia. It's on year 17. It's $33 billion in. It's supposed to cost $11 billion. It's on the order now 7 or 8 times per kilowatt hour wind and solar, which can go up in 1 or 2 years. It has weapons proliferation, meltdown risk, etc. So this is what the Biden administration is proposing: more nuclear, more bioenergy, more carbon capture, more direct air capture. I mean, they're also doing a lot of renewables too, so I don't want to totally say it's bad. I mean, a lot of renewables, but they're also putting money into these other things that are not useful at all.
Okay, great. Thank you very much for your answer. In the meantime, we have some questions in the
I can't hear you.
chat box, but maybe we have Alessandro Massi Pavan who wants to ask you a question. I think we can unmute him so we can let him speak.
I think
please.
You're still muted.
Yes.
Please unmute Alessandro, please.
I think Alessandro is already connected.
Yes, but he is not unmuted yet. Please try again.
Okay.
Alessandro. Okay.
Yes, please, Alessandro.
Yes. So thank you very much, Professor Jacobson, and thank you very much also to the University of Padua, to Alberto Bertucco for organizing this really great seminar. And so thanks also from the Interdepartmental Center Giacomo Ciamician from the University of Trieste. We work on energy, transportation, and the climate change. And I was reading your book, and I found really brilliant the solution that you proposed in order to solve the problems that we have in the world today. And moreover, I found many of the answers to several of the questions that commonly arise in the mind of skeptics. And there are really many. But something that I could not find, but you already mentioned a little bit about it, I would like to ask your opinion, if you can deepen your opinion on this, is the role of critical minerals in the transition to renewables, and especially with reference to the energy storage.
Yeah, sure. Well, it's interesting. Focus on lithium for a minute, because we'll need a lot of batteries, and you need lithium for a lot of good batteries. There are many alternatives, of course, to lithium for batteries. There's sulfur batteries, there's iron air batteries. But anyway, with lithium, well, first of all, when we change the energy infrastructure, we're changing the industry energy infrastructure too. So all the mining itself will be renewable in the end. So no emissions from the mining itself. Now, in terms of lithium, there's actually ways to extract lithium that require zero mining, new mining. For example, the Salton Sea in California, there have been surveys that there may be enough lithium in the Salton Sea alone to power the entire United States, provide enough batteries for the entire US, for example, maybe even much of the world. And they can extract that with no new mining. The reason is there's already geothermal electricity being produced in the Salton Sea. There's actually a place in Germany as well where you have the same situation. And when you're doing geothermal electricity, you're already bringing up a brine that contains lithium. And so that fluid that already contains this lithium, you can extract the lithium from the fluid without any additional mining. So that's one way. That's a second way to make the process cleaner and reduce mining, is combining lithium extraction with geothermal electricity production. Now, you will need, there will be cases where you do need new mining, but as I mentioned, it's orders of magnitude less. There was a study recently that looked at that very issue of looking at a fossil fuel energy infrastructure versus a renewable energy infrastructure. And the people who claim that, oh, you need a lot of mining and that's going to cause a lot of damage with renewables, they almost always ignore the fact that you have continuous fuel mining with fossil fuels. In fact, I had to write an opinion editorial recently addressing a climate skeptic who was claiming that fossil fuel mining is less than renewable mining, but they totally ignored the fact they were just talking about the infrastructure. They were ignoring the fuel extraction. So there was a recent study that found that over a lifetime, over 20 years, mining for a renewable infrastructure in Texas would result in, they had some number like 20 million fewer tons of earth moved compared to fossil fuel infrastructure. So this is, yeah, you're not going to get rid of mining. We can make it cleaner, have better practices, but it will be a lot less mining than with fossil fuels.
Thank you very much.
Sure.
Okay, so there are a couple of questions from the chat box. The first one comes from Lorenzo Pattelli. Now, let's see if we can unmute Lorenzo so that he can directly ask his question to you. Otherwise, I can read it. But
yes,
Lorenzo, please, are you there? Yes, please. Go ahead.
Available. Yeah, I'll say. Okay, so thank you for the talk, and my question was somehow related because I would like to learn a bit more about what potentially what alternatives are there to batteries, and if these are viable or realistic, if they can provide a viable energy density storage, let's say. And in particular, you mentioned at the beginning compressed air, I think liquefied air as well. With that, I think we could, of course, this can be then used to generate electricity again, and also cooling. And this was my thought, because as it expands, I think it should also cool down itself, So this could be a combined beneficial effects, for instance, during summer, when the cooling needs are highest.
You're correct. Well, there are these many options, and the market will determine which ones are going to be the most efficient in terms of the costs. But I should say that the most common type of electricity storage today is, aside from hydroelectric dams, which are basically big batteries, is pumped hydro. And pumped hydro is the largest. And then batteries are growing. And then, as I mentioned, there are many different types of batteries, not just the lithium. But yeah, compressed air is another option. I would say it's going to fill a niche. I don't think it's going to be large. I mean, one of the ideas for compressed air is when you have a wind turbine, you can actually have a small storage container nearby, so that when you have extra electricity, you can then compress the air, and then when you need the electricity, you can expand it. And so they're local sites. So the compressed air storage, like underground in caverns, that's not going to be very large because there are only a few places that you can do that effectively. So it's more likely for compressed air, you might have these storage containers. And if it's great if it works, if it's economically competitive, that would be great. I'm guessing it'll be probably a niche, maybe same with the liquid storage, but who knows? One of these technologies the cost may just be so low that it'll take off. I mean, batteries are nice because they're simple. You can put them pretty much anywhere, and the costs are coming down. If the cost of battery systems get to less than $60 per kilowatt hour of storage, I think the game is over. I think we can go forever with that, with less than $60 a kilowatt hour. Right now, it's on the order of 100 to 150 or so per kilowatt hour. But it's estimated that by 2030, 2035, if not sooner, it'll be down to 60. And so that would make it very easy to provide 100% renewables everywhere. But if one of these other technologies like compressed air or gravitational storage, where you lift concrete blocks when you have extra electricity and you lower them when you need electricity, if those come down in cost, that's great. We support all of those. But I can't say which one is going to win out right now.
Great. Next question comes from Giulio Guggia. We have already a couple of more questions.
Everybody's muted again.
Can you hear me? Can you hear me from the maybe? Okay.
Can you hear me?
Yes, I can hear you.
Okay. Good evening to everybody, and thank you for the conference. I also wanted to ask something about energy storage. I come to understand this scenario will need a lot of energy storage, and from some researches I did, I found out there is no a very competitive type of bulk storage. The only very versatile and efficient energy storage we have is batteries. For example, particularly lithium batteries, which can work on vehicles and so on. However, I think we should consider also the the strategic materials we need to make these batteries very efficient. And I'm thinking about the mines in Congo, which is I think it's almost the only place where we can find cobalt for lithium batteries. And I wanted to ask if you consider these needs in your articles. And also, I appreciated the taking into consideration of the social gain in the transition. However, I wanted to ask if you considered also the loss of jobs, which could result, for example, for the cut in use of traditional energy sources, and the decommissioning cost of power plants which are already in operations. Thank you very much.
Thanks. Yeah, with regard to materials, yeah, we've kind of discussed that, but in terms of cobalt specifically in the Congo, well, we definitely want to institute good practices. So we will need cobalt. I think there are also alternatives. There are other ways that we'll have batteries that might minimize the use of cobalt. But in a place like the Congo, we need to institute better practices. But I don't think, we're going to have to do something. We're going to need a transition. This is, so we cannot say, well, we're not going to mine cobalt in the Congo because of because the practices aren't good now. We just have to improve them. So we'll have to find a way to make it work. That's the bottom line, because otherwise we can't transition unless we include storage. If not, we'll have to go to other types of storage. So those are the alternatives: either go to other types of battery storage for cars, for example, or find a way to make the current mining practices better. So I don't have an answer to what's the best way to improve the conditions. I can just say that that's what we need to focus on, but we will need these materials. And I have a feeling, we can find cobalt other places as well. It's just that that's where most of it's being mined right now. But again, overall, the amount of mining of everything will be orders of magnitude less. So that cannot be used as a reason for not going forward with this. Because if we don't do this transition, we're stuck with far more mining, millions of air pollution deaths per year, which is not acceptable. And then global warming, which is causing horrific problems. So there is no choice but to move forward. So we just have to find a way, rather than argue that, well, we shouldn't do it. So we have to just find a way to do it better. And with regard to jobs, yeah, there are going to be job losses in some industries. We do find more job creation in other places. So like a place like West Virginia in the US, where it's mostly coal mining, they're already starting to train. In fact, that's part of one of the good things that President Biden has done is actually a job training, retraining for example, coal miners or oil workers. So we will need to do that. There will be some tough times for some people, but in the end, there will be an improvement for more people. And so again, we need to focus on the overall picture and try to make it, try to have a safety gap or safety measures for those who lose their jobs to make sure that they don't fall too far behind, and then they can be retrained also for newer jobs. So nothing is going to be easy, but again, we need to march forward, because otherwise if we don't march forward, we're really going to have we're going to have worse consequences than if we try to march forward. But thank you again. Those really good questions.
Thank you, Mark. So next in line is Giovanni. I think we can unmute you so that you can directly ask your question. Let's see if Giovanni is still there.
1 minute, please.
Let's just, there you go.
Okay. Giovanni, please go on.
Giovanni, please.
Okay. Can you hear me?
Yes. Thank you.
Okay. Hello, Mark. Congratulations for the whole work that I guess there is behind all this data you are bringing to us. And what about offsetting? Because we surely will not be able to meet the UN goals of 50% emission less within, let's say, 1930 and 100% within 1950. So the offsetting, it will be a very important, let's say offsetting, I mean the compensation of CO2 reduction, right? Definitely, I agree with you that the capturing it's very difficult and very expensive. But let's not forget that we have up there in the atmosphere already something like 1,000 gigatons that are the actual cause of the climate change already. So we will have to capture somehow those tons, right? What do you think?
So, well, you mentioned we might not get 50% renewables, let's say by 2030, but if we want to use direct air capture, well, first of all, I do support natural direct air capture, like growing trees, reducing deforestation, better carbon practices for land. So natural methods I'm fine with. But if you want to use direct air capture, you need energy, right? And even if that energy is renewable, let's say it's coming from wind, well, that wind, if you're not using it for direct air capture, what would you be using it for? You would be using it to replace a coal plant or a gas plant. So if you use wind to replace a coal plant, you not only eliminate carbon dioxide from the coal plant, but you eliminate the air pollution from the coal plant, and you eliminate the mining of the coal, and you eliminate the coal infrastructure. Whereas if you use that electricity just for direct air capture, all you're doing is reducing some CO2, not reducing air pollution, not reducing mining, not reducing infrastructure. So the social cost benefit of using that wind is going to be far higher. In fact, it's 10 times higher to replace a coal plant than to run direct air capture. So it actually makes it more difficult to solve the problem. The reason we won't get, I mean, if we can't get more than 50% renewables on the grid, and we use, and if that's because we're using the renewables for direct air capture, that means we're actually slowing ourselves down, because you actually get more CO2 reduction by taking that same wind to replace coal than you do to direct air capture, because direct air capture is not really efficient either. And so it's an opportunity cost. And so actually we've looked at this, and there's actually no case where it's better to use direct air capture than to just take renewables and replace fossil fuels with them. It's always better to do that. Even if you get to 100% renewables and zero fossil fuels, then the question is, well, should we spend money and use energy for direct air capture, or should we reduce deforestation, reduce methane from landfills, from rice paddies, reduce CFC or halogen emissions, reduce nitrous oxide? These are other low-hanging fruit that's actually easier to do than direct air capture. Direct air capture is really another reason for the fossil fuel industry to stay in business, because they just say, let's offset, and so we can keep running our coal plant or gas plant because we're offsetting with direct air capture. I think you're still on mute.
Thank you.
Now it's Andrews Gedrimas' turn. I hope the pronunciation is correct. We are going to unmute Andrews in a second, and then you can ask your question directly to Mark. Andrews, are you there? Can you hear us? Oh, okay. Well, alternatively, I can read Andrew's question if Andrew is not able to speak directly. Can you hear me, Mark?
Yes, I can hear you.
Okay, so Andrew says, great presentation. I wanted to ask Professor Jacobson in regards to, can you hear me? Sorry.
You're muted.
Okay, sorry. There again. So I want to ask Professor Jacobson in regards to solution for weeks without wind. Is it really the hydrogen solution for maritime industry long-haul transportation? Is also the hydrogen practically of storage, space, etc.? This is the question.
Yeah, well, when you have weeks without wind, so we looked at, as I mentioned, intermittency of wind and solar in 145 countries, broken into 24 world regions, and looking every 30 seconds. And so it's really, if you don't have wind, you need it's a combination of solar, storage, some geothermal, hydroelectric. So it's really a combination. We found that even, well, first of all, if you have weeks without wind in one place, you don't have it without, I mean, there is wind, there's always wind somewhere in the world. Now, on a continental scale, there's also always wind, even though it's not zero, even if, so you don't have weeks totally without wind, you might have weeks with low amounts of wind. But we found, in fact, we did a study for Europe where I looked at individual countries, keeping the grid 100% renewables and stable in each of the individual countries of Western Europe, like even down to Luxembourg. I mean, we were able to keep 100% renewables continuously in Luxembourg, which is a tiny country, powering itself, but also in Spain, France, Norway, Denmark, Netherlands, UK, etc. And then we looked at combining them, interconnecting them. So it's always cheaper to interconnect countries, but you can also keep the grid stable in individual countries because it's a combination of wind, solar, geothermal, hydroelectric, tidal wave, and also storage. And this is why the battery storage really helps to do that. You can get a week of battery storage just by concatenating 4-hour batteries together. And so, and you also have big hydro dams. I mean, especially, Norway is like a big battery because it has so much hydro. Switzerland also has a lot of hydro. So by combining these places with hydro with a battery storage and combining with solar and wind, if the wind's not blowing, often the sun is shining. Well, sometimes though you don't have either, and that's where the storage comes into play. So you have to size the storage to make sure you don't have the power out. There's always some size of storage. Then it comes to the question, okay, what's the cost of the storage? So that's when, if the cost is less than $60 a kilowatt hour, you can add huge amounts of storage, huge, without any problem. And you don't need much space for it. And you can keep the grid stable. So that's the solution, is adding sufficient amount of battery storage together with the other types of storage. And you have heat storage and cold storage and district heating as well. Actually, the more district heating you have, the cheaper things are as well. So it's really a combination of all these factors. In terms of hydrogen, hydrogen for long distance marine for shipping, that's good for fuel cells. We're proposing using hydrogen only in fuel cells, not burning hydrogen. But we did an analysis transitioning long distance ships, long distance aircraft, military equipment, all sorts of tanks and armored vehicles to hydrogen versus electricity. And electricity you can do for some, but you can do everything with hydrogen in terms of practicality based on published technologies. So yeah, for long distance ships and planes, we use hydrogen fuel cells.
Thank you. So next question comes from Professor Massimo Guarnieri, and he can address the question directly from the room here. Maybe you
Where is the microphone?
The microphone is here at the camera, so let's see if we can see. There you go. This is Massimo Guarnieri. There, you can ask your question.
That is me. Okay. Thank you for your presentation. I'm Massimo Guarnieri from University of Padova. I have a question about, again, energy storage related to grid power quality and stability services. In order to provide stability, we need faster response, faster technologies, and lithium-ion actually is a good choice from this point of view. But in the last month, it is emerging the need for also to provide not only so far response, but also long discharges, long duration, in excess of 4 hours, which is the typical limit used for lithium-ion. I think you do not find any lithium-ion battery that is rated for more than 4 hours. So what can be, for instance, I know that the Fraunhofer Institute for Chemical Technology is ready to publish a paper on a experimental study in Germany showing that longer times are needed for give stability in the order of 10 hours or so. And I think compressed air and pumped hydro are not suitable for this because they have not fast response. So do you have any analysis on this kind of demanding service, challenging services, which must be either fast in the response and longer in the duration? Thank you.
Yeah, in fact, well, that's a recent study. We looked at concatenating batteries. So we have long duration battery storage. Just if you take 4-hour batteries and you put 2 together, you now have 8 hours of storage. Put 3 together, you have 12 hours, etc. So just concatenating batteries creates long duration storage. That's the solution, and it works. I mean, I have, because I've had it in my own garage. I have 4 batteries concatenated together. And so each is a 2-hour battery. It can give me 8 hours of storage at the peak discharge rate of 1 battery, or it can give me 2 hours of storage at the peak discharge rate of 4 batteries, or anything in between. So we already have long duration storage. So we don't need new technologies for it. In fact, we don't want a 100-hour battery or a 20-hour battery. I'm not saying we don't want, I mean, the thing is you want the batteries both for the duration and the peak. And if you have just long duration storage with a low peak, that's not helpful for getting the peaks. And if you have just short duration with high peak, then that doesn't help either. But concatenating the batteries gives you both long duration and high peaking, and then you can do anything in between. So that's really the solution, is just concatenating batteries. So we don't need a new technology, in my opinion. Now you're muted.
Okay, thank you, Professor Jacobson. Next question comes from Vanni Lughi. I hope we are going to be able to unmute Vanni Lughi. If Vanni, are you there? Can you hear us? Okay, otherwise I can read Vanni's question.
I can hear you, and I can speak if you want.
Perfect. We can.
Yeah. So thank you very much for your talk. Very enlightening, very clear, with so many data. So there's been a lot of talking about the mining issue, and you have said that, and I agree with that. That mining, if we switch to renewable, is going to be reduced by orders of magnitude, and yet this is overall. But for specific materials, for specific critical materials, the mining is actually going to be increased by orders of magnitude itself, like 1 or 2 in the case of lithium, for example. So I guess I have a more a comment, and I would like a comment from you too. I think that switching to a very hardcore circular economy on this type of materials is going to be key in order to allow the energy transition, to make these energy transition possible. So I would like you to comment on this, on the idea of recycling these critical materials, and if you have looked into it, and if you think it's possible, and to what extent, in terms of both, well, essentially in terms of scalability as of now. And the other question is more general. What do you think the key bottleneck is for the energy transition? Where do you think we should put all our money right now?
Right. Well, yeah, in terms of recycling, there are already companies that recycle 95 to 97% of the materials in batteries. So Redwood Materials is one. J.B. Straubel, who's one of the founders of Tesla, he quit Tesla and then started this battery recycling company. And they already do this. They already recycle all the critical materials. And there are other companies actually that do it as well. So this is already happening. And so that's going to alleviate some of the mining needs, or hopefully a lot. Because, yeah, we'll need one-time mining, but then that, whatever that cobalt or lithium that is mined, it will go back into batteries, hopefully, and other materials for hundreds of years before we need even new mining. So I think that will help a lot. And sorry, when it was your second question, what was that again? It was about the bottlenecks. Yeah, bottlenecks. So yeah, the biggest bottleneck I see is this all of the above policy. Well, aside from education, most people are not aware of what's possible. And so I think there is this, the fact that most people aren't aware, then they think that there's nothing, it's not possible to transition. They're skeptical about renewables as a result. So education, I think, is the number one bottleneck. The number two is that there are a lot of people pushing a lot of technologies that are not very helpful. And so that distracts from the solution, and it's like an opportunity cost, and it makes it harder to transition if we have so many competing solutions and money going to so many different things that are not going to be so helpful. So I think that's another bottleneck. In terms of practical things, transmission distribution is not going to be easy to add fast. It's not a technical problem and not even a cost problem. It's more of a zoning issue. So you'll probably end up, well, to keep the grid stable, you either need a lot of transmission distribution or a lot of storage or a mixture of the two. I think storage is going to win out in the end, mostly because it's hard to put up a huge amount of transmission distribution, new transmission, especially long distance transmission. So that could be something that slows things down, because it would be nice to have a good mix of both transmission distribution and storage.
Thank you very much. I think we are approaching our deadline, 4 o'clock Italian time. So we will take one last question from Enrico Nobile. We are going to unmute Enrico. Can you hear us, Enrico?
Yes, I can hear you. Can you hear me? Okay, thank you very much for this opportunity. I would like to thank the organizer, and particularly I'd like to thank Professor Jacobson for this very interesting presentation. I know that my question might not be very popular here. I'm talking about nuclear energy. I know and I agree on the fact that nuclear energy might not be considered as a possible renewable energy source alternative for different reasons: nuclear waste, safety, proliferation risk, etc., and so forth and so on. However, there have been a fair amount of claims about the forthcoming compact, standardized small nuclear reactor. I think you heard about that. So I'm just wondering if you don't think that they might play a role, at least in the first phase of the energy transition, because of some of their advantages. They use a limited amount of land, they are intrinsically safe, they can use the present grid infrastructure, and so forth and so on. What is your opinion? Thank you very much.
Well, before large nuclear reactors, there was actually a lot of development of small reactors, and the reason they were abandoned was because of economies of scale. So I think in terms of costs, they're going to find that they're the same or more expensive than the larger reactors. They're not even being planned to be ready until like 2028, 29, 30, and everything in nuclear is always pushed back. So we need 80% of the problem solved by 2030. And if we have a technology that won't even be ready by then, and that'll even be just a demonstration scale, it's not very helpful. And then there's no evidence that it doesn't have all these other problems. I mean, some of the reactors are being touted because they use higher refined uranium, that's a higher refining percentage, but then you're closer to weapons grade uranium. And you have these small modular reactors, you can move around the world. So the weapons proliferation risk becomes even larger. Whether there's a meltdown risk, we don't know. There's going to be, you just need as much uranium mining. So the mining problem is still there. And the ones that claim that they don't need so much mining because they use, or they have higher concentrations of refined uranium, in those cases, again, they're weapons grade, closer to weapons grade. So there's really, I don't see any difference between these types of proposed reactors and the large modular reactors, except that they're easier to spread around the world and create weapons problems. And the risk, the risk is unknown, especially when you have a bunch of different companies that have a bunch of different standards. We don't know what the risks are. So I think from estimates of cost, the costs are going to be similar. So, maybe they'll be take a little less time to put up, because they're more modularized, but maybe not, you just never know. So I would not, we have technologies today that we know work. And again, I think we should focus on what does work, keep our eye on the ball, and try to solve as much of the problem as possible with what we have. Costs are coming down for everything that's related to renewables, including batteries and wind and solar, and even geothermal and CSP and electric vehicles. So we should just focus on things that we know are safe. Why focus on something that has so many risks associated with it and so many unknowns when we have technologies that do work? So that's, I would say, don't invest in this new nuclear.
All right. Thank you again, Professor Jacobson. And I would like to go to the conclusion of this meeting. And well, I express, of course, our gratitude from University of Padua, University of Trieste for your lecture. And we enjoyed that. In my opinion, we are headed to a fossil fuel-free world, and we must run in that direction. And the problem until a few years ago was about technologies. As I understand, nowadays technologies are already available, and the problem is deploying them rather than developing them. I was also very much interested about your comments about things that are usually thought as a must in this energy transition field, such as bioenergy or carbon capture and sequestration. And this is again another interesting point that you talked with today. So while thanking you again, and thanking all the people who connected and spent this hour for this lecture, I would like to invite all of you to attend, all of you Italians, of course, to attend the events of our center, Levi Cases. In the future will be 3 events in May. On the other hand, Professor Jacobson, we are really grateful to you for your time, for your commitment, for being with us, even though in the distance, and making us to understand better your message and your research activities. So if you would like to add something, that's finished, that's over. And please.
No, I just want to say thank you for inviting me, and it's really great questions and good engaged discussions. I learned about some of what people are thinking about and some of the issues that are important, and so it's great that everybody's also on board with transitioning to renewables here. So thank you again. I really appreciate it.
So have a good time. Good luck and bye-bye. From Italy. Arrivederci. Bye-bye.